go. Think about that. You all rolled 10 times. Think about the disparity in the numbers that I was calling out. A lot of you had 1 finger up, a bunch of you had 2, there were a few of you that had 4 fingers up, Tiff had 5 fingers up. So think about that. She rolled a die 10 times, and half of her rolls were 1s. And we haven't even talked about, good, Christina just wrinkled her nose a little bit. Because she's like, that sounds kind of interesting, doesn't it? That seems interesting to roll a die 10 times and have half of them be 1 before we even get to the 2, 3, 4, 5, and 6. Doesn't that seem kind of strange? Good, that's why I'm collating our data together to see if that truly was an outlier due to random chance, or we can take a look at her die later to see if something's up. You see what I'm getting at? If it's showing 5 out of 10 rolls as a 1, maybe that die has more 1s on it than it should. Or maybe it just happened to fall that way, because it does happen to fall that way sometimes. We'll come back to that. All right, 2s. Same thing. Hands up, number of 2s that you got. 2, 6, 7, 9, 13, 14, 15, 16, 21, 22, 23, 26, 27, 28, 29, 30. Thank you, friends. Again, I didn't get any 5s that time. There was 1 4, a few 3s. But that same kind of gut feeling chewing away, like, interesting. So now, Tiff, you have 7 rolls accounted for, all 1s and 2s. Very interesting. 3s! Let's see some 3s. How many 3s we got? We got 3, 6, 8, 10, 14, 15, 18, 19, 20, 23, 26. Love it. 26. 4s. How many 4s do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 15, 16, 17, 18, 19, 21, 25, 27. Love it. 5s. Let's get some 5s on the board. 3, 6, 8, 9, 10, 15, 17, 20, 4, 26, 27, 28, 29, 30, 31, 32. I don't think I counted Tiff yet. 32. Good. Now, technically, I should be able to do this without asking you all. So I can count how many of you there are times 10, add those up and subtract from that number. But that's too much work. How many of you got 6s and how many did you get? And I probably screwed 5. There's 5 6s, interesting. 10, 12, 17, 19, 24, that's 4, 24, 26, 27, 34, 34. Okay. And I can tell right away I added wrong because it doesn't, that last column doesn't sum to something that ends in a 0. That's okay. It's totally fine. What does it sum to? I don't know. Sum up our frequencies. And I do want to actually use this number momentarily. We get 15, 20, 28, right? Carry the 2. So that's 6, 8, 10, 182, 188. Check my math on that, friends.
Sure, yeah. 188.
188. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 19. Okay, I'm short by 2. That's okay. I can live with that. I can live with 2 errors. I blame myself. It's not you guys. All right. Now here's how I want you to add a column right now, if you'd be so kind. Get 2 out of there. I want you to add a column we haven't talked about. We talked about it a little bit back in the day. Remember what relative frequency was? Remember this? If you don't, that's okay. Call it percent, because that's all it is. What I'd like you to know, what I'd like to know now is to the nearest percentage, what percent of the rolls were 1s? That's why you need this guy down here. That's why you need this guy down here. Does that make sense? Now, if you want, can I show you a TI trick that might make this a little bit easier? So everybody, if you'd be so kind, let's start by graphing our data. Let's get, just like we would at anything else. Just like we would anything else, let's graph our data. Okay, stat, edit. 6. And then take a look at it. Take a look at it once you've got her up there on the L1 and L2. Do a zoom stat. I'm going to finagle. It's got a weird number of bars. I'm going to finagle the window to make it fit better. It's got an x min at 1 and x max at 6.555. I'm going to make that x max at 7, which I know doesn't seem to make a whole lot of sense. You remember why I have to go to 7? Exactly, Christine. It has to have a width. So that last bar is going to go 6 to 7. That's going to count the number of 6s that we have. It's the way the TI is set up. So it's going to be 0, 1, 1, 2, 2, 3. So if you make it 7, that's good. And then make the x scale a logical 1. This actually makes the most sense as far as scaling. When you press graph, there's our distribution.
Oops, oh wait.
So make sure you press graph, not zoom static. If you press zoom static, you erase all your good work. What do you think about that? How would you describe that distribution if you had to pick a name for it? If you had to pick that data. Say it again, Danny. Bimodal. Oh, I like it because it's got the 2 tops. You got over here and over here. Bimodal. I like that. I like that. Hold that thought. That thought. Good. U-shaped. Patrick, you're gonna say U-shaped. Like opposite bell. Very nice. There's a distribution called a Weibull distribution. W-E-I-B-U-L-L. That actually does this, and it's used very often when they talk about how much money we should warrant or how long we should put guarantees on products for. You guys ever purchased like an extended warranty on something? Because machines oftentimes have what's called an infant mortality rate that's very high. Like if something's going to break, it's going to break right in the beginning. And then if you make it through that infant mortality rate, there's almost no chance of it breaking until it gets very old when it shoots back up again. So you get these cool U-shaped distributions called Weibull. I'll have you guys look at that later on in the course because they're kind of fun when you talk about stuff like that. Like when can you expect something to break? And how should you approach the warranty period on that as such? Have fun. Good, very good. So unimodal or bimodal, U-shaped, inverse bell-shaped distribution. Good. Let me ask a question. If we were to do this 10 more times each and put our data in with this, would it still look like that, do you think? Good. One say yes, one says no. The rest of you looking at me like, I don't know the answer to that. Because that's the strangest question I've heard all week. And your week is young. I'll ask more. Maybe. Yes, maybe, no. 3 awesome answers. 3 awesome answers. Impossible to answer without more data. We'll get to more data momentarily. Hold that thought. Let's get the relative frequency. Oh, what were you going to say, Walter?
Oh, I wasn't going to say.
You were going to say anything. Okay,
well, if we did it another 10 times, statistically speaking, when we have the same odds come up.
So what Walter is actually agreeing with Patrick. You're agreeing with Patrick.
More in line with that.
Good. So you're saying you're agreeing with Patrick. Patrick said no, it's not going to look the same. It's going to look different. But you have like a 1A, if you will. Walter's saying that if we do it more and more and more, these are going to start leveling off and becoming the same. And you're making an assumption I like a lot. We're going to come back to that. Give me 5 minutes to come back to that. Thank you, Walter. Very nice. Very nice.
All right, equally likely as anything else.
Oh, it's okay. No, oh, who's that? I'm sorry, I heard a voice. Madeline, go.
I said that is equally likely as anything else.
Okay, hold that. I love this equally likely. Good, we'll come back to that because this is where we're getting back to probabilities. We're actually getting into the land of statistics and probability together. Finally, shaking hands, and it kind of coincides nicely with your second project. Let's set up the relative frequency column. Now, one way to do that, of course, is to take that number divided by 188, that number divided by 188, that number, and so forth and so on. But you can use your TI like a spreadsheet, too. So go back to your stat editor, clear out L3. I gotta remember that it starts with 68.
Okay.
Yeah, leave L2 where it is. Now, here's how you use it like a spreadsheet. Put your blinker up on top of L3. Now type L2, second 2, divided by 188.
Oh, I should write that down. Hold on.
Okay, see what I just did? Now when you press enter, it will do just that for you.
Wait, L2
divided by 188. So the divide by symbol, 188. And as long as you're on top of L3, it'll then fill underneath with the percentages. If you're getting an error, that just means you weren't on top of L3. You have to put the blinker up on top of L3 to get this to work.
Enter after that.
And then enter after that, and it'll fill up with percentages.
Oh, lovely.
So I get 21% here. I get 16%. I'm going to round these off to 2 decimals just to make life easy for us. 14% here. 14% here, arguably. 17. 34 is going to be 18%. Let's see what that sums up to. The sum of the relative frequencies is going to be, it should be what?
100.
It should be 1. Let's see if we got any rounding error, which sometimes happens. So we got 7, 11. I think we're okay, right? 15 and 15. I think that's 30, so carry the 3.
Yeah, that's a flat 100.
It's a flat 100, yeah? 1.00. Now sometimes it doesn't. Sometimes it comes back 0.99 or 1.01 because of the rounding error. But on average, it will be 1 exactly. And if you used all the decimals that you aren't really entitled to, it would always come up to 1. You're not entitled to all those decimals though, unfortunately. But it has to sum to 1. If you think about why, 39 divided by 188 plus 30 divided by 188 plus 26 divided by 188 plus 27 divided by 188, plus, this is getting annoying, I know, 32 divided by 188 plus 34 divided by 188 is 188 over 188, which is 100%, or 1. Is this believable-ish? Now, what you just created, friends, actually has an extraordinarily important place. It's probably the most important thing in statistics, honestly. If you had to point to one thing and say, that's the most important thing, it's the idea of these two columns together. These two columns together. This is what sets your car insurance rates. This is what sets your health insurance rates. This is what sets your life insurance rates. This is what sets how much you pay for cell phone coverage. This is what sets pretty much anything you pay for on a regular basis with premiums. This is what does, not this particular one, my God, imagine that was based on rolling a die. But the idea of this kind of mathematics, setting up this kind of a table, is what sets those rates. And that's what I want to kind of start talking about today while linking it back, is the idea of probability distributions. Oh yes. Oh yes. Probability.
So we can technically use the information we're getting today for the project.
You can, but we can get better data.
All right.
And it hints at what Madeline and Walter are talking about.
Okay.
You can, but it's much, much better to get more of the same data. Probability, I suppose, right? Probability distribution. You won't need it for the project because everything you need for the project is already contained in there.
I know.
I'm not trying to be a jerk.
No,
I'm not trying to disagree with you. It definitely can't hurt, but I'm not sure it's giving you anything extra that you already don't have in that document.
reassurance, maybe.
Well, maybe. Well, it will definitely help you understand some of the stuff more. That's for sure. That's for sure. Especially what Walter and Madeline are just talking about. And I think what Patrick was hinting at as well. Here's the deal. There are two kinds of them. There are discrete ones, and there are continuous ones.
Oh, back to like week 1.
Oh yes, it all comes full circle, right? It all comes full circle. That's why that's the link between where we were and where we are. I feel like Doc Brown in Back to the Future. Here's where you were, here's where you're going, where you will be. Marty! We're going to take a pause on the continuous ones. It's recording, right? Get the Doc Brown, good. We're going to take a pause on the continuous ones for right now. The problem with continuous ones is it makes an unnecessary amount of agenda that I don't want to put you guys through. The agenda is you get confused with what goes in the left column. Discrete makes it very, very easy. So we're going to focus on these for right now, and we'll add the continuous ones once you guys get the discrete ones under your belts. And it'll take a while. It'll take a while. We're going to spend like 3 weeks on this, building this idea up. Lots of rolling dice, spinning coins, and things like that. And then eventually talking about my chickens, which will bring the whole thing home, which is tied to Max's pumpkins in some way. So you're going to get inundated with data sets that are all going to be discrete. Then we'll make the leap over to continuity, because then it's just one thing to change versus like 3 things to change. So a discrete probability distribution is really, it's either a t-table, it can also be a graph, or it can also be an equation. But it's usually just a t-table. Usually the easiest way to view it is just in a t-table. That describes an experiment. Now I'm going to use this word experiment extraordinarily loosely. You talk about experiments. You've all done experiments in science classes. You plant a bunch of flowers, and half of them you yell at, and half of them you play classical music to, and then you see after a month which ones are growing better. Which ones are growing better? The ones that you yelled at, they get more carbon dioxide. I have no idea how that experiment would come out. I have no idea how that would come out. You would think the classical music, I have no clue what it would be.
Mythbusters did it, it was classical.
It was classical music, Mythbusters. Bastards. Did they yell at them, or did they just not play music to them?
They played an audio track and they had a control.
Oh, control, so no talking. So that'd be a confounding variable if you yelled, stupid plant, give it a carbon dioxide level. Now play punk rock and play classical and see what happens. That might be interesting. Anyway, But the idea is you run an experiment to see something, see what happens. Maybe you don't know what's going to happen, right? We just did one in 244. Give cyclists a bunch of caffeine before they work out and see what happens to their heart rate. Now, what you would expect, give a bunch of people caffeine, what would happen to their heart rate? Christina just danced it for me. It's going to spike. What people noticed, and what the researchers noticed was, it did spike when they were sitting there ready to go. And it spiked at the end when they were at a full sprint. But it actually dropped halfway between, over and over and over again. Therefore, became an outlier, became something for us to look at and go, what the hell just happened there? So what we discovered was you should take small amounts of caffeine at sub-max levels of exertion, and it actually drops your heart rate, making you a more efficient cyclist. Who would care about this? Professional cyclists. Because they're looking for every possible advantage, ergo doping and other things like Lance did. But here's potentially illegal, I think caffeine's actually mitigated too by the UCI. But nonetheless, it was an outlier, and the experiment showed a surprising result. You see what I'm getting at? So you do these experiments to see what's going to happen. Statistics should not be used to prove things in general. It should be used to uncover things. Like, oh, that's cool. I wasn't expecting that. Or let's see what happens kind of thing. Whoa, whoa. Why is my son an outlier? Well, for many reasons. But why is he an outlier on his bike? Oh, because you put him on the what the hell is it called? The Strider. Thank you. Put him on the Strider early on, right? So the idea is you can describe an experiment. Now, the best way, I like the T-table method, personally. Because you're very used to it after 5 weeks in my class and also all your previous mathematics before this. So your T-table ends up looking pretty classic. It's got an X column, which is all values, there's an L in there, all values of, I'm going to use a term here and then define it in a minute, of the random variable. We're going to define that term momentarily. That's an important term in this class for the remaining of the remaining half we have together. You put all the values of the random variable in one column, and in the other column, you put the probabilities. So they're going to look like that. It's going to look like this. So you have a T-table where you've got a left column and a right column. In the left column, you're going to have all values of this magical thing called a random variable. That sounds terrible, because it has the word variable in it. And I know you're all kind of still gun-shy about Math 111, and variables, and f of x, and logarithms, but there's nothing like that. It's nothing that bad at all. All you've got to do is ask yourself, what possible values can the experiment take on? It's much easier than Math 111. For example, if Gallup calls 100 people and asks each person, do you approve or disapprove of the job Congress is doing? There are 101 responses to them saying yes. 0 can say yes, 1 could say yes, 2 could say yes, 3 could say yes, all the way up to 100. So there's 101 values of that random variable. After they've done 100, right? They've done 100 people, they've asked 100 people, yes or no, do you agree with how Congress is doing? There's 101 possibilities for the number of people that are going to say yes. There's also 101 possibilities for the ones that are going to say no. There's also 101 possibilities for those who say I choose not to respond. Anywhere from 0 to 100. That might be confusing. I'm saying 101. That's because you have to include 0. 0 up to 100. We didn't have a 0 with our die because you can't roll 0. But all you have to do is think, okay, what could happen in this? What could happen in this situation? Okay, when I let my bike go at the top of the hill from Grandview down, what possible values of time could I have when I cross the 200-foot mark on that tape? But that gets a little trickier because that's continuous. But the idea is you have to sit at the beginning and say, okay, what values could that take? The idea of a random variable, just don't get too hung up on what that is. All it is by definition, a random variable, and we're usually going to call it x in here, it just makes more sense. Variable. We're usually going to call it x, and I try to use a capital X because that separates it a little bit from the idea of a data point, little x. I try to keep them separate so you can, because you do different things with them in general. There is some overlap, but we tend to treat these guys a little bit differently with what we do with them. And all it is it's some value somehow dependent on chance. It's some value somehow dependent on, oh my goodness, hydrate my friend.
I'm getting over that. Now
I
it's
know you
cold.
are, I know you are, I know you are.
But it's good now.
It is. I know. It sounds awful as you're healing. I know it does. It sounds terrible when you're healing. I gotta fix the duct tape on this too.
Would you have us do?
Nah, that'll do. So what part of our variable was dependent on chance? Some of it was and some of it wasn't. So you grab your die and you go to roll it, and you know what's going to happen. You do, don't you? I mean, to some degree you do. Can you roll it? You're going to roll a 1 to a 6. So you do know that. You're not going to roll a 13. There's a 0% chance of a 13, a 0% chance of it, a 0% chance of pi, 3.14. You know there's 6 values that you're gonna get. So you know the values of them, 1, 2, 3, 4, 5, 6. What you don't know is which one you're going to get on that trial. But that's not what a probability distribution aims to tell you. It doesn't aim to tell you what you're going to get on that trial. It aims to tell you what you're going to get on average over repeated trials. How often have you guys heard me say, well, on average, your class did it? Tiffany's like, all the freaking time. I had you 105 until I sit for 10 weeks. That's the idea. When I give your exams back to you, for example, I show you the class average, the class median, the class graph. And I say, on average, I'm stoked. Because that's all I can do. I can't look at each individual one of you and give you an individual assessment on how you're doing. I can do that. With a progress report, I do that. But when I give them back to the entire class, I give you a group look. That's what a distribution is. It's an overview. It's a way to identify outliers. We can use the same tools we already have. We can find an average. We'll do that momentarily with our single die roll. There's all kinds of cool things you can do with it. But what it doesn't try to do is micromanage. It tries to talk about, on average, what's happening. So the random variable are the things that can happen. And the probabilities are simply the rate at which they happen in the experiment. That's all they. So how often does a 1 occur? Well, in our experiment, it happened 21% of the time. How often does a 2 occur? In our experiment, it happened 16% of the time. 3 occurred 14% of the time. 4 occurred 14, and so forth and so on and so forth and so on. So the random variables are paired off in the first list, and the probabilities are paired off in the second list. Check this out. Regraph, but don't take away the first graph, but turn plot 2 on. Turn plot 2 on. So leave plot 1 on. Plot 1 is your beautiful histogram. Turn plot 2 on. This might seem a little stupid. Make it a histogram, but make it L1 and L3, not L1 and L2. Make it L1 and L3. And then just hit graph. And just hit graph. Now, mine are on.
The graph?
Graph. But what's the problem?
Window? It's weird.
Right. We can fix the window. The trick with fixing the window is we're going to have a hard time. Your graph is there. But you got to remember the frequencies of your graph are between 0 and 1. The relative frequencies. The frequencies, excuse me, are between 0 and 188. So watch this. Press trace. Press trace. You see how right now you're on the tops of those bars and you can scooch right and left and get back and forth on those bars?
Yes.
Now press the down arrow and scooch right to left.
Oh, hey.
They're down there.
Oh, wow.
They're down there. They're down there. It's just that they're so far down because of the scaling. So let's take a look at them now. Okay. Back to our window. That's okay. We'll fix it, Madam. We'll fix it. Back to your window. Leave everything the same. Change your Y min to 0. And change your Y max to, make it 0.3. I think that will do. You see why I'm picking 0.3? The biggest Y that we have percentage-wise is 0.21. So I think 0.3 will be a fairly good look at what we need to be. And then you can change the Y scale if you want to something else. And then press graph again.
What'd you put it to your Y scale?
I've changed it to 0.05. Now, do you see something that looks familiar?
Yes.
See this guy right here? Does he look familiar?
Yes.
Doesn't he look familiar? What does he look like? It's the same as the previous histogram was in shape. Because all you did with that previous histogram was divide everything by 188, and it brought it 188 times closer to the x-axis, essentially, is what you're doing. It's a Math 111 trick. What are these lines back here?
continuation of the graphs.
That's the other histogram going up to 188, which is now way the hell above it. If you want to clean it up a little bit, you can turn that graph off and then just look at our graph. But now, those are the percentages. There's no difference in shape. You're actually getting the exact same idea with that graph that you did with the previous one, but you have a percentage versus a frequency. Why would we want a percentage versus a frequency, do you think? This is a tricky question. Why would you want a percentage versus a frequency?
Because probability can be like put out onto the general population rather than the statistics, which is just the frequency.
Totally true. The statistic gotten from one single sample is limited to that one single sample. But if you can apply a probability across a general population, which is easy to do with more and more and more collected samples and smaller margins of error, this is what you're going to end up seeing as I move it around. This is what you're going to end up seeing most of the time. For example, how many of you have heard that teenage boys pay more for car insurance than teenage girls? I've often heard that. Why is that?
They have a higher rate of accidents.
They have a higher rate of accidents than teenage girls do.
They actually say that's not true anymore with the introduction of cell phones.
Oh.
Girls text more.
Because girls text more. I didn't know that.
I can see that.
I didn't know that.
Yeah.
When you say girls text more, see, this is where it gets interesting. I hear girls text more, but I don't know how many girls we're talking about. And that's why we don't care. We have a rate of texting or a rate of accidents. So, in other words, all of these insurance ideas are based not on this column, but they're based on this column over here. You see what I'm getting at? That's why we care about these distributions of probabilities now. We can apply the exact same statistics that we were using, but to probabilities. For example, on average, what are you going to roll when you roll a die? You're going to roll a die, right? On average, what are you going to roll? I don't know. Let's find out. Let's find out. We have our data, right? We've got our data. Let's run one bar stats. One bar stats. Yeah, right, exactly. You see what I just heard? Oh, that's right. Because it's so easy to forget. We have all the tools we've got. They're not gone. They're not gone. On average, one bar stats. Do L1, L3. Yeah, do an L1, L3, because that's where our frequencies are. On average, what do we roll?
3 point.
Let's go back to our experiment over here. I'm going to slide this over this way.
Okay, I
But
gotta quit.
okay, I've got.
Hold that thought.
I've had lines going up since I started
That's
having
okay.
a hard
That's all
time.
right. We just got to change your window to 0.3. It's this guy. We make him look at L1 and L3 instead of L1 and L2. There he is.
There we go.
You was looking at your original data, Madeline. Not a problem.
Okay, thank you.
Hold that thought, Danny. I'm not saying we should use this average. I'm saying this is what we do on average. Danny's upset with this, and she should be. Here we go. Here we go. Sample X bar, we're getting about 3.5. 3.5. I'm going to come back to this in a second, too. I'm going to come back to this X bar right here. Because I want you guys to notice something else.
There's no standard deviation.
Say that again nice and loud, Renee.
There's no standard deviation.
Where did the standard deviation go?
I don't know.
Okay, good. I don't know, but I like this class even less right now. There's no sample standard deviation. There is no sample standard deviation.
Well, we put in L3. So
We did, and if you put in L2, if you put in L2, you would get a standard
would we?
deviation.
Okay.
But L2 is treating this as a sample, and L3 is actually treating it like a population. And that's why there's no sample standard deviation. It disappears because it's assuming in 21% of the time in the population we get a 1. 20 or 16% of the time in the population we get a 2. And we know that's not right. We don't have enough data to stand for the entire population. We don't have enough data to stand for the entire population. But hold that thought, friends. Hold that thought. We're going to come back to this. We're going to come back to this. 1.8. That's about 1.8, right? I want to come back to this guy too. I know we don't look at him very often, but I do want to come back to him momentarily. I'm going to ask a question I asked about 15 minutes ago. If I asked you guys to roll your dice 10 more times each, would we get the same thing that we got right here?
We don't know.
And we don't know. We could, we might not. It might start changing the shape. We just don't know. So what I've got instead of having you guys roll again, I set up a little experiment of our own. I think we can see this. Christine, I might take on you for a moment to see if we can see that okay. turn this off. How's that look up there? Is it decent? Okay. So what you see up here is a little experiment I set up. I'm going to roll a die with the computer. Rather than have you guys roll like 100 more times, I'd like to have like thousands of rolls. That would be like my ideal, right? Thousands and thousands and thousands of rolls. What I've got right now with Excel set up is I've got a command in this cell called rand between. Now I know I've had you guys mess around with this command before in a quiz that I gave you guys a few weeks ago, the in-class quiz, where you had to do the samples. Last week, which you'll get back hopefully on Wednesday when I get the hammer all squared away. This is the same command in Excel. When you type rand between 1 comma 6, what you see is a random number between 1 and 6 generated. And what I've set up here is I've set up the TI. You can't quite see it. The screen is still not quite right. You can't see the... Yeah, I need to adjust the... I put in a work order for this. There's more screen that you can't see right now, unfortunately. Yep, I can minimize it. There we go. How's that? That's better, right? So there's the actual current roll.
You could also set print area.
Oh, that's good too.
Although I don't know if you could...
That's okay, this will work. This will work just fine. If I press F9 again, it rolls it again. That time, I rolled a 1. I press F9 again, that time I rolled a 6. That time I rolled a 2. That time I rolled another 1. And that time I rolled a 3. So I just rolled the die 6 times. I just rolled the die 6 times, and the Excel has kept track of what I got each of those times. In the pie chart, it's showing me the results. Now, let's think about this logically. Let's think about this logically. Tiff's glaring at me. I love that. That's good. Logically, we're going to come back to this. I'm not done yet. Logically, we should have been able to figure out what the right column of this distribution is without doing this experiment, shouldn't we have?
The right column.
This right column. We had the left column, which is 1, 2, 3, 4, 5, 6, which we did figure out. Did we really have to go through all the effort that you guys went through to figure out what percentages should be here?
No.
Honestly, no, because assuming the dice are fair.
Then you have an equal chance of getting any of the numbers at any one time.
Absolutely. I'm going to call this relative frequency experimental. Just add that to the top. Don't erase it. Leave it in there. Add it to the top. But to the right of that, I'm going to add another column. Relative frequency or probability of X. Can I put that in? I'm going to use some shorthand that you've been using in your projects. P for probability, parentheses, X. What the hell is X? Oh, X is the number of pips that we show. So, probability, don't vomiting. That doesn't mean function. That's not f of X. That's just what's the chance of getting X number of pips? Well, it's P of X. It's P of X, but it doesn't mean take an X and stick it into a function. It just means what's the chance of getting that many pips. So the probability of getting 1 pip, well, we saw it as 21% when we did our experiment, but it's actually 1 in 6. Should be 1 in 6, right?
Yeah.
The probability of 2 should be 1 in 6. The probability of 3 should be 1 in 6. And 4 should be 1 in 6. And so forth and so on, yeah? Mm-hmm. They should all be 1 in 6. Which adds up to that always has to happen. That always has to happen. The sum of the probabilities in any given experiment has to sum up to 100%. Because if you've got over here all of the mutually exclusive outcomes for an experiment, and remember what mutually exclusive means? This has been about 3 weeks. You may have forgotten. It's okay.
That one thing does not affect the other.
Good. If one thing happens, the other one can't. So if you roll a 1, you can't roll a 2, nor a 3, nor a 4. If you roll a 6, you can't get a 5 or a 1. So you've got boom, boom, boom. You've got 6 mutually exclusive trials. Outcomes, not trials. Outcomes. Then the sum of the probabilities has to be 1. Because 100% of the time, you're going to get a 1, 2, 3, 4, 5, or a 6.
You can always get shrinkage to rounding, like by 1 or 2 points.
That right there is what we're seeing here. This is roughly 17%.
Right.
A little bit shy of 17%. We didn't see that. We saw exactly 17. Well, actually, these were all rounded off anyway. But nobody actually hit 16.6666%. But that's because our sample has error in it because of the sample. What's the only way to make the error in the sample get less?
More.
More. Well, glad you asked.
Right. Of course you are.
Now notice, I just rolled 6 times, but I didn't get one of each of the numbers. Is anybody pissed about that?
No.
Not even a little bit?
A little.
Renee's pissed. Good! You really? Only one person's pissed? I heard a little, and Renee's like, I'm pissed. I want to see every number. Patrick? Okay. No, I was going to say you're pissed. No, kind of ish, not really. Why should you not worry about that we haven't gotten all the numbers yet?
Because we haven't rolled 6 times.
But the chance of a 1 is 1 in
Yeah.
6.
Yeah.
Right.
Doesn't that mean if I roll 6, I get 1?
No.
No.
I just asked a question that has 2 correct answers. It actually does mean just that if I add 2 more words.
Or
Over time or on average, either of those 2 words. It does guarantee that I will get 1 for every 6 trials, but it doesn't guarantee I'll get it in the first 6.
Okay.
It only guarantees over time on average. This is the definition of probability. Remember from your first project? The idea of a probability in that first project was you have to watch something happen over time to establish the probabilities. That's why I wouldn't use the numbers you guys got in your experiment to describe what's going on any single die. I would have to roll lots of dice. Right then, I just eclipsed what you guys did in class, right there. Right there. Now, let me take my stapler, because although I'm pretty slick with Excel, I'm not slick at programming it. I need to use a stapler to hold the damn thing down so I can walk away from it. Nope.
Just tape it down.
Hey, what if I brought tape? That's a very good idea, actually.
I have a ruler you could probably jam in there.
It's still only gonna skew, you know me. There you go.
The stapler tends to work pretty well. Now, what I want you to do, can you see my distribution I'm talking about?
Yes.
Yeah, here's the same thing, X's number of pips right here, just like you guys had. But here's the new probability of X column. And what's it beginning to hover into?
17.
They're starting to all close on that 1 in 6.
One more to go.
Look at the pie chart.
Woo, it's really hardly, you know.
Beautiful.
Yes,
La, 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 la. It's-
I would definitely agree with you, Danny. It's absolutely beautiful.
It's beautiful.
The reason I like pie charts, most statisticians hate pie charts. I can't think of a better graphical representation of this than a pie chart. Because it's like a pizza cut into 6 equal pieces. And that's, go ahead, Tim.
And we've been dealing with it since like the 2nd grade.
That's true. But statisticians are like, no, you can't have pie charts. No, they're ineffective. No, they're ridiculously effective for certain things. I'm not saying they work for everything. I'm saying they work great for this. Now, it's not perfect. Look at the numbers in here, friends. Just like us, they have too many 1s. I don't know if you can see that's that's 486. Down here it's 470. Oh, they're catching up though. And that's what goes on. We always saw in the beginning, was a rush on 1s that would have gotten eaten up, 2 words,
Over time.
over time. And that's the beautiful thing about probabilities. You have to have the probabilities happen over time in order to truly see them behave. And that's where actuaries get their tables from. The whole statistics started with this guy named, I think it was Richard Grant or Gaunt, terrible last name. But his job was to figure death rates. I think it was in London back in like the 1800s or something. And what he did was he went back over time and looked at tables upon tables upon tables and looked for consistencies across the tables. He was the first data miner, if you will. Please, Renee.
Is that why one study taken at one time is incomplete?
Yeah, you have to see it replicated if you want to start calling it the standard. And this is why I harp on margins of error so much. Your statistics, these 0.21s, 0.16s, 0.14s, 0.14s, and so forth, those are statistics. They should have a margin of error on them. They should have a margin of error on them. And because you only have a sample size of about 188, that margin of error is actually pretty wide, probably like 6 or 7%. So if you apply a 6 or 7% margin of error to these numbers, you can't say that they're not 1/6 anymore. Because 1/6 is going to be between those margins of error applied to the middle. Just like we did back in the day. If you apply a 6 or 7% to this, 1/6 is in there. So you can't say it's not 1/6. Now, if I got like a 0.01 here and a bunch of other stuff over here, I'd be like, what the hell's going on? Something's going on. I gave you guys the wrong dice. Then I start looking at the outliers and be like, something's up. Something's up. but nothing seems to be outlierish. Yeah, it's not perfectly 1/6, 1/6, 1/6, but it sure would be if you let it run long enough. Now, I know these don't sum to 100%. I don't think they do anyway, but that's because of a rounding error. They sum to very close to 100%. And roughly what you're seeing, let's see if I can stop it at an even multiple of 600. Let's see, 600, I think I missed it.
72?
72, thank you. We'll stop it at 72. The idea is, even if I stop it exactly at 72, 3, 4, 5, 6, 7, 8, 9. There. At 7,200, how many should there be if we were seeing exactly 1/6 across the board?
7, wow.
An equal number each, 1,200 each, right? Is that right, 1,200? 1,200, 1,200, 1,200, 1,200. Yeah, 1,200 each. Did anybody come up exactly 1,200?
No.
No, but look, 1205, 1208, 1210, 1176. That's down by 24, but it's off by 24 out of 7,200, which is way less than 1%. 1208, 1193, it's not perfect, but it's way more perfect than our estimates were. And it rounds down to the nearest decimal. Isn't that beautiful? Now, what you can then do once you see this is you can refine your experiment in your estimations. Let's turn this off and go back to your TIs. And let's refine our estimate.
Okay.
Let's refine our estimate. Go back to your stat editor.
Okay.
Stat editor. And remember that beautiful L3 stuff that we did up there? The L3?
Yeah.
We put in 0.20745 and blah, blah, blah. Change them all to 1/6. Change them all to 1/6. 1/6. 1/6. 1/6. 1/6. And so, I don't know why I'm saying this out loud. Apologies. Now, why can we do this? Because you've just run an experiment almost 10,000 times. And you've noticed that the results that came back are all 1/6. So you can make the assumption that the dice that are being rolled in Excel, and most likely the dice that are being rolled by you guys, are fair. We're seeing just as many 1s as 2s. Because we saw 1 out of every 6 times a 1. If you ignore the sequentialness of it and look at it as a whole, we saw 1 out of 6 times. Tiffany got 5 out of 10. It's extraordinarily rare to happen in 10 trials. But it's almost guaranteed if you look at it over a long period of time. It's almost guaranteed to happen at some point. That's the kind of the cool part about it. Ready? Go back to one of our stats again on L1 and L3. Go ahead and crunch it. Notice what you got. What's your average?
I'm sorry, what are you saying, 1 bar stats?
Yeah, one of our stats, I used L1 and L3, LaWanda, because I'm using the data, 1, 2, 3, 4, 5,
Do we
6.
still want to use the L1
And,
or 3?
oh yeah, for sure, for sure. And I'm using L3, which is those percentages we just put in, the 1/6, 1/6, 1/6.
So what do I hit? I hit bars and
Then L1, comma L3. Usually we do L1, comma L2.
Stat and then one
Over
variable
to
stat.
calc.
Yeah, stat calc.
Yeah, not under edit, but under calc.
Right. Just like we do for any weighted average. This is just a weighted average. It's just a weighted average like we were doing before, except now we have percentages instead of frequencies in there. So over to calc, 1 bar stats, which is the first choice.
Stat.
L1, comma L3.
Oh, 1, enter.
If you roll a die,
That should be L.
on average, what do you roll?
Okay, stat.
You roll 3.5 on average. To which Danny was upset 20 minutes ago. She said, wait a damn minute. Wait a damn minute. What does it mean, average 3.5? You can't roll a 3.5. You can't roll a 3.5. So what does it mean to average a 3.5 on a roll?
3 or 4.
Well, here's the deal. If the probabilities happen with equal likelihood, every time we roll a 1,
You roll.
we also roll a what? A 6. A 1 and a 6 average to 3.5. Every time we roll a 2,
1 and a 6.
we also roll a 5. And a 2 and a 5 average to 3.5. And every time you roll a 3, you also roll a 4. And they average to 3.5 as well. And this is a function of the fact that this distribution is even across the board. We'll start with this one again on Wednesday for sure. But don't feel bad about that average of 3.5. In 1990, there were 2.5 kids per family in America.
Right.
That just means if you added up all the random variables, number of kids per family, including 0, and you ran the exact same calculation, the center of the distribution was at 3.5. Friends, There's the histogram. There's the histogram of 1/6, 1/6, 1/6, 1/6. Where's the balance point?
I don't know. Right there? I
It's the easiest one I've ever asked you to do. It's right there.
It just looks so
And that's-
normal.
When you say normal, what do you mean?
Just flat and
That's called a
straight.
uniform distribution.
Okay.
It's symmetric. It's perfectly symmetric. It's basically infinitely modal because everything has the same frequency of occurrence. I won't even talk about modes. But it's symmetric, which means the average is right in the middle.
Okay.
And the middle's 3.5. It just so happens the average isn't one of the data points. But that happens. We know that happens. We know that happens. More on this on Wednesday for sure. I don't want to leave this one go.
Yeah, I don't want
Oh God, yeah, we're not anywhere near done. This will take us into next
I
week.
think something's wrong. If I was to see that, I would be like, oh no.
No. Because our data that we experienced in class has the real fluctuations. This is what will happen to it on average. We saw that in Excel with the pie chart. The pie chart evened out. If I was to make that a histogram, it would look just like this.
Okay.
Fair?
Okay. Yeah.
Okay. For Wednesday, there's a few things up there right now. Let's talk about that. You got your project. So make sure you get that knocked out. There are 2 quizzes posted. One of them is on, I promised you guys 2 quizzes for next week. I wanted to make sure or this week, I guess. One of them is on relative position. By all means, knock that one out if you want to. One of them is also on outliers, but we didn't finish that till today. So if you want to maybe push that one back till next Monday, that's totally fine. All right? Technically speaking, we should also go over homework.